Homework 4, Part B2, we're going to be starting at an initial steady state with our initial concentration coming in and our volume coming in, which would be 0.01 meters cubed per second and the concentration of 1 mole per meter cube. And then our flow rate will increase by 10% and our concentration flow will increase by 25% if the tank has the constant cross-section area, and we'll simulate the concentration and the liquid level. I think I'm just wasting time here. For homework 4, part B2, we're going to start at our initial steady state with our concentration and our flow rate coming in, and then we'll increase it by 10%, 25%, and then the rest is same as the first, and then we'll see how the concentration and the liquid level change over time. So we have numpy, SciPy integrate, SciPy P, and our subplots, our gravitational constant, our initial flow rate coming in times 1.1 or increased by 10%, our initial concentration, the size of the hole, our initial not the initial concentration, the cross-sectional area, the size of the hole draining, our initial concentration coming in, increased by 25%, and our concentration of the tank at the initial flow rate is going to be equal to the concentration coming in. So the next thing we need to do is get our initial height of the tank. So our H0 will be equal to our AD squared. This will be divided by, this is not right, sorry, our Q in initial squared divided by AD squared, and then that will be multiplied by G, or 2 and G. So that should get us our initial height, and it should be the same as our first problem here. Yep. All right. And then we can have our time limit, so our T end is going to be equal to 1,000. And I suppose we can just make our T-plot already up here. So NP length space from 0 to 1,000, and we'll do, oh, not 1,000, Tn. We'll do 1,000 points. All right, now that we have this, we can move on and define our function. We'll call it dv dt, and we'll use a vector. So it's a function of time and our vector, and our vector will be equal to the concentration and the height. So we already have our Q in, so we need our Q out. So our Q out will be equal to our size of the hole times 2 times G times H, which will be the square root of all that, right? And then we will have our dH dt, which will just be equal to our Q in minus our Q out divided by the cross-sectional area. And then we'll move on to our dC dt, or our change in concentration, which will be equal to our Q in times our C in minus our Q out times our concentration of the tank. Because it's well mixed, our concentration of the tank is equal to what's leaving. And then this will be divided by our cross-sectional area. Then subtracted from this will be our change in height times our concentration once more. And then this entire equation will be divided by the height, and that will give us our equation for dC dt. And now we'll return we have our CA first, so DC dt will go first, and then DH dt. All right. Now we can use our solve IVP. So our results, solve IVP of dv dt. Our time range will be from 0 to t end. Our initial values are going to be C0 and H0. And we dense output equals true. True. And our method, spread out. See what that does. All right, so that works. So then our CA and our H will be equal to res.solve or tplot. Now we should be able to move forward and plot these out. So our fig make subplots, rows equal 1, cos equal 2, fig dot add scatter, and this will be our x will be equal to our time, tplot, sorry. Our y will be our concentration. The mode for this will be lines, and we'll name this CA. Then we specify, so this will be row equals 1, column equals 1. See if that works out so far. All right, that looks good so far. Then we can add in our height, big dot add scatter. Our x will once again be our t-plot. Y will be our height, road times name H, and this one, row 1, column 2. All right, so once our initial flow rate is increased by 10% and our initial concentration coming in is increased by 25%, we can see that after some amount of time, it looks to be about 600, it'll come to a new steady state at which the concentration in the tank's 25% higher and the height has increased by about 1.2, 1.15. So that would be our new steady state. All right.